Hi, I'm Marga Manterola, Director of Engineering at Observability. I'm here today to share with you my excitement about eBPF, the current and future state of our Hive. I got into eBPF 2.5 years ago when my former colleague Alban, author of Inspector Gadget, asked for help in delivering an eBPF workshop for KubeCon. I'm a big believer in the fact that teaching is the best way to learn something, so I jumped into this opportunity. I learned what eBPF is, how it works, and what it can do. And my mind was blown. The ease with which I could get the information I needed and understand what was going on in the system was something else. Using eBPF allows us to get kernel-level results without needing to be a kernel hacker. One of the things that got me hooked was how I could write a short and simple BPF trace one-liner and get the exact information that I was looking for. And that's only one tool among many. Every year we get more new tools based on eBPF, solving different problems or different aspects of a problem. And then we don't need to learn a domain-specific language anymore. We can just use the tools as they are. You are watching this talk as part of the eBPF Summit, so you might already be familiar with some aspects of eBPF. eBPF makes the kernel programmable. It makes it easy for developers to dynamically create code that hooks into the kernel to enhance observability, networking, and security. But why has eBPF been so revolutionary? Why is it so much better than writing kernel modules? There are a bunch of reasons. The first one is safety. The verifier checks that the code we write is safe and runs in a sandboxed environment. With kernel modules, it's easy to do something wrong and cause a panic, or worse, who knows what crazy havoc we might create. With eBPF, our screw-ups are limited to the BPF program itself. Another important feature of eBPF is portability, particularly after the introduction of BTF, the BPF type format, which makes it possible to write BPF programs that work on any BTF-enabled kernel without having access to the kernel headers. This lets us ship pre-compiled BPF programs to any BTF-enabled kernel without having to recompile them, just as we would for normal applications, but not the case for kernel hackers writing kernel modules. And yet another important aspect is the language diversity. While we still use C for the BPF code itself, instrumentation can be done in other languages like Rust or Go, leading to better integration with the rest of our system. All of this has led to more and more tools getting released each year that make use of eBPF to dynamically program the running kernel and provide efficient networking, observability without instrumentation, effortless tracing, and real-time security. Now, I want to come clean with something. When we talk about eBPF, we usually mention that it allows programmers to code the features they need in the kernel today without waiting for these changes to be merged in the kernel, released, adopted by Linux distribution, and finally reach consumers 3 to 5 years later. And this is true. Using eBPF allows for faster iterations, letting eBPF developers have a role in what the kernel is doing instead of having to always wait for kernel developers to get those features out. However, one thing that is often left out of this explanation is that eBPF has also been evolving for many years. Since it first got added in 2013, there have been a lot, and I mean a lot, of changes that have enhanced what we can do with it. When looking at requirements of an eBPF tool, it is pretty common for it to say that it needs at least some specific kernel version to work properly, maybe 4.19 or 5.4 or some other version. Some tools try to keep compatibility with previous kernels by implementing some missing functionality in user space. But that means the same operation running in an OS with one kernel version can take a lot more CPU time in another version. Or some functionalities might just be disabled when the version isn't high enough. The good news is that by now the basic eBPF infrastructure has mostly been stabilized, and while there still is significant innovation going on at the low level, the kernels provided by the stable releases of common Linux distributions include BTF support and can be used by most eBPF tools. However, before trying out the latest and greatest, it still makes sense to check the requirements and verify that your current kernel version is supported. So what are these tools that I keep mentioning? There are quite a bunch already, and I'm sure the list will keep growing as time passes and more people come up with new ideas of how to take advantage of what eBPF has to offer. So let's now do a quick overview of the current state of the eBPF landscape. We can basically split the tools into three categories. One important group has to do with networking. We can do a lot of cool networking operations with eBPF, in particular by making use of the XDP or Express Data Path. XDP is a framework that allows us to process packets at high rates directly in the kernel instead of having to go to user space and back. The decision on whether to allow or reject a packet is done by an eBPF program running in the kernel, leading to much better performance. In this group, we have tools like Cilium, a networking solution for Kubernetes. Cilium has been using eBPF from the very beginning, providing a comprehensive and efficient networking layer. Operations like applying networking policies, mapping services to the IPs of the pods in that service, or connecting separate clusters with a shared virtual network can all be done very efficiently thanks to eBPF. Another well-known networking tool based on eBPF is Ktrun. Ktrun is a layer 4 load balancing library that can handle extremely high traffic in an efficient way. On top of these well-established applications, there are a few other emerging tools in the eBPF networking space, like LogCLB, an external load balancer for the edge, or Merbridge, a service mesh acceleration tool. Next, let's look at observability and tracing, which is the category with the most tools. eBPF allows our programs to hook into specific events, like the execution of a syscall or the return of a function, and provide visibility as to what's going on without needing to change the code of the program that we want to observe. This can let us monitor, profile, audit, or debug our programs without any additional instrumentation. One of the first tools developed for doing this is eBPF Trace, which comes with its own domain-specific language. This allows us to write simple scripts or even one-liners to get the data that we need out of our system without needing to write or compile the eBPF code ourselves. And there's also kubectl Trace, which uses the same DSL and applies it to Kubernetes clusters. Another scriptable tool is Pixie, which captures telemetry data in Kubernetes clusters. It comes with some pre-created metrics, and we can add our own as needed. It also includes its own UI to visualize the data that it captures. On top of these generic, scriptable tools, there are quite a bunch of specialized tools that have been designed to solve specific needs. For example, Pyroscope and Parka are tools created for continuous profiling, allowing us to find why things take longer than expected while our programs continue operating. And Wacky is a tool that provides interactive profiling and debugging, letting us interact with the source code while we profile it. The tool I mentioned at the beginning, Inspector Gadget, is another observability tool for Kubernetes. It comes with an array of easy-to-use gadgets that help trace, profile, snapshot, and generally gather information about what's going on inside Kubernetes clusters. The list goes on. There's also Hubble, which provides network observability for Cilium, Kepler, a Prometheus exported for energy-related metrics, the Apache Skywalking rover, a metrics collector for the Skywalking project, and others. The next step, after detecting that something is happening, is taking action. This is where the third broad category of tools, security, comes in. Tools in this group can either log, alert, or even block execution when certain events take place. The power that eBPF brings to these tools is that we can have our tools check for certain actions without having any internal knowledge of what the application is doing. In this group, we have tools like Falco that applies rules based on system calls executed on our machines and can trigger alerts when those rules are violated. Tracy, that captures events as they happen and can detect suspicious behavior, and Tetragon, that combines monitoring the system for specific events with runtime enforcement when the established rules aren't followed, as well as more domain-specific solutions like KubeArmor for container-based applications or Pulsar for Internet of Things applications. If you are looking to develop a new eBPF tool, the eBPF ecosystem also includes a number of projects that help with creating and managing these tools. You can access the power of eBPF from C, Go, Rust, Python, and Lua. The BCC project provides a toolkit for easily creating eBPF programs and integrating them into other applications. The Leaf project provides lifecycle management of eBPF applications, and the Bumblebee project provides a packaging format for distributing eBPF programs as containers. And there's even an eBPF for Windows project aimed at allowing developers to apply the same principles that created eBPF to the Windows kernel, including some shared APIs. As you can see, the eBPF ecosystem is becoming quite broad. I'm sure that a list like this will be significantly longer next year. If you want to learn more about any of the projects I mentioned, you can find a more extensive list of open source tools that use eBPF with links to websites with more information at ebpf.io/applications. And if you have developed an open source eBPF tool and it's not listed there, make sure you send a PR to the site adding your project so more people can learn about it. Now, before we close, I want to emphasize that our community is continuously growing. No matter where you are on your journey today, whether you are starting to try out some of these tools, you are developing one of them, or you're a kernel developer adding some cool new enhancements to eBPF, your contributions are welcome. A bright and exciting future is ahead of us, and your participation will make it even better. Thanks for watching, and I hope you enjoy another day of amazing eBPF talks at the summit.